start the hello. Yeah, we will start the session in a couple of minutes. Thanks for your patience. I hope I am audible. Just say a yes or a hands up, like if I am audible or not. start in a couple of minutes. See if one or two people might join. Okay, then we will start today's session. So yeah, good evening everyone. So I am Diljit Datta. I am a research scholar at IISc. So I'll be taking today's second week's problem solving session for this course optimization methods in civil engineering. So I hope you have gone through the class lectures that which are already uploaded in the NPTEL profile, NPTEL portal. So I will be just going through some basics of the methods that have been taught in this week regarding linear programming and the simplex method that is used to solve linear problems, linear optimization problems. First I will just brush up the concepts and then I will solve a couple of numericals so that you can get your concepts clear. And if you have any doubts, just feel free to ask me anytime. Okay, then let's start. I think in the last class I just taught like what is linear programming. So linear programming is like it's optimizing linear. Yeah, I will do that. I'll go into simplex method, but initially I just brush up the concepts and then we'll solve numericals. In that process, I'll show how to fill up the values in the simplex table. Just wait for some time. Okay, so linear programming is like optimizing a linear program, a linear problem, and it is subject to some constraints which are also linear. So the constraints, number of constraints and a number of variables, it can be equal, or the number of constraints may be greater than number of variables and the number of constraints might be less than number of variables. So based on these three situations, there are three possible solution scenarios. So one scenario is when m is greater than n, where m is the number of constraints and n is the number of variables. If the number of constraints is greater than number of variables, in that case there will be m minus n redundant equations. So we can ignore those equations and solve our problem based on the remaining equations. If m is equal to n, in that case there will be a unique solution or there might be no solution. That depends on the type of the constraints. And thirdly is m less than n. So in that case number of variables is greater than number of constraints, and in that case there will be infinite number of solutions, and among those solutions we generally need to find one optimum solution, that is a maxima or a minima. So this is the basics of linear programming. So a feasible solution is one that satisfies this matrix formation. I have shown the constraints that like in this way: a1 on x1, a1 to x2 up to a1 and xn equal to b1. So if we write this in a matrix form, it will be a into x is equal to b. So this is the matrix form of the constraints, and x is greater than equal to 0. So this is one of the primary constraint that all the decision variables must be non-negative. So a solution that satisfies all this criteria is called a feasible solution, and a basic solution is one where after setting, suppose a basic solution is obtained in the third case where m is less than n. So we will have only m constraints and n variables. So there will be n minus m variables that will be the non-basic variables, and by setting these variables to 0, we will get a solution based on the remaining m variables. So that a solution that is obtained based on the m variables are called the basic solutions. And the and the variables that are in the basic solution forms the basis. So this is, in this case, this is a small example. There are 3 equations and there are 4 variables, that is x1, x2, x3, x4. We can set one of the variables to 0. Here I have set x4 equal to 0. So once I have set that to 0, we will get the solution for x1, x2, x3, and that will form the basis solution. So what is a basis solution? It is the collection of the variables that are not set equal to 0. But while solving, we might get that value, it might be equal to 0, but we are not setting it a priori to the value of 0. Then next is what is a basic feasible solution? A basic feasible solution is that satisfies non-negativity conditions. That is, we have formed we get the solutions of values of x1, x2, x3, and if these values are greater than equal to 0, then we say it is a basic feasible solution. And lastly, the optimal solution. It is a solution that satisfies the objective function and is a maxima or a minimum. So a small a brief discussion on the pivot operation and getting pivots from the equation. So if we have this set of equations e1 to en, where e1 is like a11 xn, you can see the equations here, and en is the an1 x1, an2 x2 up to ann xn. So when we have this n number of linear equations, we can do some row operations or on the row operations on these equations, and by doing the row operations, you can also multiply each operation by a constant and then add it to some other equations. So these are called elementary operations, and by doing these elementary operations, we can convert this set of equations, that is like with all the constraints, into this form. That is where we have the coefficient corresponding to one variable as 1 and the coefficient corresponding to other variables is set to 0. And why are we doing this? So we are doing this so that we get directly get the value of each variable directly from the equation. So this changing of linear set of equations to only one variable in one equation is called pivot operation. So in this case, we can see we have for first row we have only x1, for the second equation we have only x2, and like that, and for the nth equation we have only xn. So if we write this in a matrix form, it will be a diagonal matrix with all the other elements 0 and only the diagonal elements. So this diagonal x1 into this is equal to the right hand side, that is the b1 dash b2 dash whatever. So we can directly get the values of each of the variable. So the solution for these equations is x1 equal to b1, x2 equal to b2, and like that up to xn equal to bn. So simply we are doing this pivot operation to get our work easy and in a less get our solution in a less complicated way. So now this was just when the number of variables is equal to number of constraints. We had this condition. Now there is second condition where number of variables is greater than number of constants, that is n is greater than m. In this case, what should we do? So we already have, suppose n variables. We already have n variables and we have m equations. So we have to do the optimization. To do the optimization problem. So first we'll set the basic variables, and these basic variables will be the m variables, because we already saw that in basic solution what we do, we get the solution for m variables where m is the number of constants. So we need the basic variables for m. We'll set m basic variables, and the other variables will be the non-basic variables. These non-basic variables are also the independent variables, and these basic variables are the dependent variables. So once we have done this, we will segregated the basic and the non-basic variables. We will do the pivot operation. That is, we will for each equation we will keep only one basic variable. The coefficient of one basic variable as 1, and all the other coefficients of all the other basic variables as 0. So in this way, we will get a diagonal matrix. So this is how we do the problem for when the number of variables is greater than number of constants. So this is how in this way we will get the final set of equations. You can see for x1 there is a coefficient 1, for x2 1, for the and up to xm there is a coefficient 1, and this xm plus 1 to xn are the non-basic variables, and they have some arbitrary coefficients. That is, after we do the row and column row operations on the different equations. So now we can get the solution for the basic variables by setting the non-basic variables equals to 0. If we set the values of all the non-basic variables to equal to 0, we will get the solution for the basic solution. So basic solution will be xi equals to bi dash, that is x1 equal to b1 dash, x2 equal to b2 dash, and so on up till xm equal to bm dash. So this solution is called the basic solution, and this x1 to xm are called the basic variables, and the non-basic variables are for x m plus 1 to x n. So this is about how we do the operation for like two different types of problem. One is where n is equal to m, and the other is where n is greater than m. Now we'll just take a problem, and we'll just take up a problem, and we will see how we do the row operations on a set of linear equations. So we have to do a pivot operation. We have to do a pivot operation on this set of equations. So let us mark the first equation as R0, second equation as R1, and the third equation as R2. So from what we have to do the pivot operation, what we have to do? We have to, like, for first variable x1, we have to keep the coefficient of x1 as 1 in the first equation, and for the other two equations we have to keep the coefficient of x1 equal to 0. So how do we do that? So we will do a row operation on the equations. So to the row operations, first we will get matrix get a equation, that is R01 equal to R0 by 2. That is, we are dividing this first equation by 2. We will get the coefficient of x1 as 1. So this is one equation that we get. Then secondly, we will get another equation. Now we have the coefficient of x1 as 1 here, so we need the coefficient of x1 as 0 in the second equation. So we will subtract this equation number 4 from equation number 2. In that case, we will get this fifth equation. That is, here coefficient, you can see the coefficient of x1 is 0 and there is some coefficient for all the other variables. And also we need the coefficient of x1 to be 0 from the third equation, so we will subtract this fourth equation from the third equation. So we will get this row R21 by subtracting R2 minus R01, and this is the sixth equation. So now we have done this operation for x1. So here you can see that after this row operations we finally get there is a coefficient of 1 for x1 in the first row, and for the other two equations the coefficient of x1 is 0. Now to do the pivot operation for the second variable, that is x2, we will need the coefficient of x2 as 1 in the second equation, and for the first and the third equation we will need the coefficient of x2 equal to 0. So we will again do one row operation where r12 is equal to minus of 2 into r11. So this is r11. If we do minus 2 into r11, we will get this equation. So once we get this equation, we will do a row operation by taking r01 minus of 3 by 2 into r12. So we will get the coefficient of x2 equals to 0 in the first equation. In the first equation, we will get the coefficient of x2 equal to 0 by taking r01 minus of 3 by 2 into r12, that is this equation. And finally we get this 8th equation, and lastly then secondly we also need the coefficient of x2 equal to 0 in the third equation. Here also we will again do this row operation, r21 plus 5 by 2 r12, we will get the coefficient of x2 equal to 0, as you can see here in the 90, in marked as 9. Similarly we can do this for x3 variable. For x3 we just need coefficient of x3 equal to 1 in the third equation, and we will need 0 in the first and second equation. Similarly we will do the row operation, and finally we will get a set of equations. So this is the final set of equations that we get. One is x1 plus 0 plus 0 plus 0 plus x4 equal to 2. The second is x2 plus x4 minus x4 equal to 1, and third is x3 plus 3x4 equal to 3. So we can express the basic variables as x1. We will consider x1, x2, x3 as the basic variables. We can express this in terms of x4. Now by setting the value of non-basic variable, that is x4 equal to 0, we will get the basic solution, that is x1 equal to 2, x2 equal to 1, and x3 equal to 3. So this was how we did for how we get a basic solution from a set of equations. Now in this first case we considered x4 as the non-basic variable, but we can also consider x3 or x2 or x1. So if we take x3 as a non-basic variable and x1, x2, x4 as the basic variable, in that case we will obtain a slightly different solution. So the solution will be x1 equal to 1, x2 equal to 2, and x4 equal to 1. Then third case, there is we can consider x2 as a non-basic variable and x1, x3, x4 as the basic variables. So in that case we will also get a different solution where x1 equal to 3, x2 equal to 0, and x3 equal to 6. And the final the fourth case is we take x1 as the non-basic variable and x2, x3, x4 as the basic variables. We will then, by considering this scenario, we will get one more solution. Thus we can see that for if there are n variables and m equations, we will get NCM, that is n factorial by n minus m factorial into m factorial number of basic equations, that is basic solutions. So in this case we got 4 solutions where 4 variables and 3 equations. So 4C3 is equals to 4. Now as we can see that for this system of equations we had 4 solutions, but when we do a optimization problem, suppose we have 4 solutions but we need an optimal solution for a objective function. So in that case we need to find which of the basic solution is going to be the optimum. So that is where the simplex method comes into scenario. We will see the which basic solution is satisfying or is getting the optimal solution for the objective function. I hope till now it is clear. If there are any doubts, I will just pause for a minute and you can ask me.
While doing the row operation,
Yeah.
we should compare only with that row where we are making that x1 or x2 as 0. That row only we should compare for any other two rows.
Yeah, like if you can see, suppose for like once we have transformed, suppose initially we have these three initial rows, right?
Yes, sir.
So we need first we have to set the this x1 is equal to coefficient of x1 equal to 1 in the first row, and x1
Okay.
coefficient of x1 is equal to 0 in the
Okay.
other two rows.
Okay.
So we'll do the row operations. We will get a set of 3 rows after doing these operations.
Okay.
So once we do these operations, we get the set of rows, and we'll have this transformed row. Transformed, that is first row will be transformed to this fourth row, and yeah, other two rows will be in this format.
So second and third row should be compared with the only first row. The operation should be done like that only.
Yes, yeah, yeah.
Okay. Okay.
Similarly, when you are doing for the second row and third row, the comparison should be only with the second row when you are taking the second variable. It's like depending on
Okay.
the
Okay.
variable. First we need doing for x1, so we'll be comparing only with the first row.
Okay.
When you're doing for x2, we'll be comparing the other two rows with the second row. It's like that way. Okay, so now we'll proceed to the simplex method. The simplex method is optimization method for linear programming. It was developed by G.B. Danzig in 1963. So the main concept of simplex method is to compare the neighboring basic feasible solutions and in a efficient way, that is like not complicating things too much. So this is a way of getting a optimum solution. So this is a simple linear program, that is linear problem that we have. We have a set of m constraints and n variables, and this is a objective function. Now we have written the objective function in this way because I think I have already shown in last class how the objective function. The objective function might be it might be function of all the x1 to xm also, but we are after doing the row operations we are getting objective function in this format, that is minus f plus c dash, that is in the form of non-basic variables. So the objective function will be a function of the non-basic variables finally, and we have to optimize this function. So when we are taking the solution will be if we set all the non-basic variables equal to 0, in that case xi is equal to bi dash, and xi equal to 0, like xi equal to bi dash for I equal to 1 to m, and xi equal to 0 for I equal to m plus 1 to, and that is for the non-basic variables. And for the objective function we will have the f naught dash is equal to f, that is the final optimum value will be f naught dash. And if the basic solution is feasible, that is the primary criterion of linear programming, that all the decision variables should be non-negative. Remember, it is not positive, this is non-negative, that is greater than equal to 0. So since we are getting xi equal to bi dash, therefore all the bi dash that we get after row operations should be greater than equal to 0 for I equal to 1 to m. And for the last row that we have, we can see that it is a function of the non-basic variables. We can write you can reframe this equation and write in the format, in this format, that is f equal to f naught dash plus sigma of ci dash into xi, where xi goes from m plus 1 to n, that is all the remaining variables after leaving the basic variable, that is non-basic variables. Now we have two scenarios. Now if all the ci are positive, so if all the ci are positive, it is not possible to improve the objective function value, because if we are I already told in last class also that we consider a minimization problem, that is the objective function is a minimization problem. If there is a maximization problem, we will just multiply that with -1, multiply the objective function with -1, and then we will do the minimization of that objective function. So even if it is maximization kind of problem, we will just convert to minimization only to get the solution. So the optimal, that is objective function, is always a minimization type of problem. Now here you can see we got some value of f naught dash, and if all the ci's are positive, that is all the coefficients of the non-basic variables are positive, in that case it is not able, we won't be able to improve, or like that is make the solution more negative, because all f naught is already positive, have some value. If it is positive and all the xi are get order, that is positive only. If xi's are positive and also ci's is positive, then it will only add to the solution. By adding to the solution, we won't minimize it further. So that is, we have already got the optimal solution. Now second case is if the one of the ci is negative. In that case, so if we can substitute that variable whose ci is negative, we can consider that as the part of the basic solution, and then we can also further minimize the solution. So that is how simplex method, the formulation of simplex method takes place. That is, we see which are the non-basic variables whose coefficient is negative, and we will see which is the most like least maximum negative, that is highest negative among all the non-basic variables. Then what we will do, we will consider that non-basic variable into the basic solution, is convert it to a basic variable, and then we'll and replace one of the basic variable as non-basic variable to maintain the feasibility criterion of the solution. So how we do that is how the simplex method will be doing that, and we will see it all the step-by-step procedure of the simplex method in a couple of minutes. So the maximum benefit can be obtained, that's what I told, can be obtained by making the non-basic variable with minimum negative coefficient as the basic variable. And if there is a tie, we can any one variable can be selected arbitrarily. So this is what I have written again. So we will get the solution, final solution, as this format, that is x1 equal to b1 dash minus a1 s dash into xs up to xm equal to bm dash minus ams dash into xs dash, where all the bi dash are greater than equal to 0. Now if one of the coefficient, that is a1 dash ais dash is positive, the maximum possible value of xs is bi dash by ais dash, and if ais dash is negative, in that case the maximum possible value of xs is infinity, and we will have a unbounded solution. So that is what I want to do, is the simplex method chooses the non-basic variable that cause maximum increase. No, sorry, it's not increase, it will be a decrease, because we are considering minimization problem. Maximum decrease in the objective function value. So again, just this is an excerpt from a book. I will just read through. You can hope you can understand. So once suppose we have selected one non-basic variable, that will go into the basic solution. In that case, the next question is which of the basic variable has to be non-basic. We have to replace one of the basic variable to non-basic, right? So and that it is clear that xq has increased, that is number of basic variables has increased, but we can keep only m basic variables. We cannot keep more than m basic variables, that is where is the m is the number of constraints. So and once we have increased the number of basic variables, so we need to reduce convert one of the basic variable to a non-basic variable. And how do we do that? So when this number of basic variables increase, then all basic variables must either be increased, decreased, or kept the same in order to keep the solution feasible. So any more increase in the chosen non-basic variable will make the basic variable negative only. So from the row equivalent formulation that we already did, I showed in the previous steps, we can write the value of the basic variable as this, that is xj equal to bi dash minus a dash j cube by x cube, and the minimum whatever then we will see what is the minimum value of the coefficient bj dash by a j cube dash. If we see, and we will see for which basic variable this value is minimum, and we will be replacing that value with the chosen non-basic variable. So okay, I will just show a sample problem. We will do it step by step. So we have a problem that is okay, yeah, we have a problem that is minimize this function fx equal to minus of 2x1 minus of 3x2, and it is subject to the conditions x1 less than equal to 6, x1 plus 2x2 less than equal to 10, and x1 x2 greater than equal to 0. So now we have both the constraints as inequality constraints, and both the constraints we have either are less than equal to constraints. So in that case, we need to insert some slack variables. So we will insert two slack variables, that is x3 and x4. In the first equation we will insert x3, in the second equation we will insert x4 as the slack variable. And now once we have we convert the constraints to a equality constraint, that is the standard form of linear programming. And this is the primary condition, that is x1 x2 x3 x4 should be greater than equal to 0, and this is the condition of primary condition that it is to be met, that is all the decision variables should be non-negative. Now we will start the solution by taking x3 and x4 as basic variables, and if we take x3 and x4 as the basic variables, and we will set the x1 x2 as non-basic variables. So by setting the value of non-basic variables equal to 0, that is x1 x2 equal to 0, we will have the solution x3 equal to 6 and x4 equal to 10. You can just see here x1 equal to 0, so x3 will be 6, and x2 is also 0, so x4 equal to 10. This is the just initial solution. Now we will need to optimize this based on our requirement. So how do we do that? So we will just write it in a table form. This is called a simplex table. The first column corresponds to a basic variable. I told already that the initial basic variables are x3 and x4. Now in the next 4 columns will be the x1 x2 x3 x4. These are the variables, and we will write the coefficients of these variables for the two constraint equation. You can see for the first constraint equation, it is x1 plus x3 equal to 6. Here we have coefficient only corresponding to x1 and x3. There is no coefficient corresponding to x2 and x4. So we can write it. So we have written this in this form. Then the sixth column will be the value of f. So there is no value of f in the constraint, so we'll keep it 0. Here bi is the value in the right hand side. In this case it is 6, so we mention 6. And this last column bij I will come to later after doing the operation. Now for the second constraint we have considered basic variable x4. Now we write again the coefficients, that is corresponding to x1 the coefficient is 1, corresponding to x2 the coefficient is 2, there is no x3 the coefficient is 0 for x3, and x4 again 1. Here also value of f is 0 and the value of right hand side bi is equal to 10. So I fill this, and lastly we will write the value of f, the equation corresponding to f. In this case we already saw that f is the function of the non-basic variables. I just mentioned in, I think here only, yeah, this is here f is the function of non-basic variables. In the initial case what we considered that x1 and x2 are non-basic variables, so we will write the coefficients corresponding to x1 and x2 in the f. What are the coefficients of x1 and x2? It is -2 for x1 and -3 for x2. So we write -2 here, -3 here. There is no coefficient of x3 and x4, so it will be 0 and 0. And the value of fx will be 0 because fx will be 0 since we are considering x1 and x2 as a non-basic variables, and to get the basic feasible solution we get the value of, we set the value of non-basic variables as 0. So initially fx equal to 0. Now we see that we can further optimize this solution because we can see there is a negative coefficient, that is ci value is negative for the non-basic variables. That is this condition, that is if all the ci are positive, it is not possible to improve the solution, but if there is a negative ci, then we can improve the solution, and the improvement can be done by choosing the non-basic variable with the minimum negative coefficient as the basic variable. So in this case we can see the coefficient of x2 is -3, that is the most negative, so x2 will go into the basic solution. Now the question arises, if x2 is going into the basic solution, it has to replace one of our basic variables, right? So how we will select that? So for selecting that, the first criteria we will see the coefficient of bi by aij, that is we have this bi and corresponding to x2, and that will divide by the coefficient corresponding to x2 for both x3 and x4. Now for the first case, here it is 6 divided by 0, it will be infinity, and for the second case it is 10 divided by 2, it will be 5. So in this case the minimum is 5, so x4 will go into the non-basic solution and x2 will go into the basic solution. Okay, so now once x2 goes into the basic solution, the coefficient of x2 in the other equation should be 0, and the coefficient of x2 in the second equation, that is where x2 is 1, in the basic, in the coefficient of x2 where in the equation where x2 is the basic variable will be equal to 1. So what we do, so once x2 is, we can replace x2 in this basic variable, so the first equation will remain the same, there will be any change here, and since the coefficient of x2 in the first equation is already 0, we need not change the first equation. So the first equation will be as it is, whatever we have from before. Now for the second equation we need the coefficient of x2 as equal to 1 because x2 has come into the basic solution. So we'll divide the second equation by 1, we'll get the first value as 0.5, 1 by 2 is 0.5, 2 by 2 is 1, and 0 by 2 is 0, and 1 by 2 is again 0.5, and bi 10 by 2 is 5. So we will get this value. Now
sir, can you repeat once again, sir, this step?
Okay, the thing is that here we have You understood this part, right? We have to
Yes.
replace x2 into the basic
Yes.
solution,
Yes. Yes.
and x4 will come into a non-basic because x2 has
Okay.
the least this smallest value for it is bi by
Okay.
aij.
Okay.
So once x2 goes here, that means what? In this equation, x2 is the basic solution that I already told, right? In when there is a when mm, okay, suppose you see this, okay, this equation, this first two equation, this is equations for n variables, but we have only two variables here, that is
Okay.
x1 and x2.
Okay.
If x2 goes into the basic solution, before x2 was not in the basic solution, so in
Yes.
that case x2 can was in this part. So here in that case x2 can have any coefficient in both the equations.
Okay.
But once x2 goes into the basic solution,
Okay.
here in this case it went in the second equation, so the coefficient of x2 in the first equation should be equal to 0. So we'll
Okay.
do the row operation so that in such a way that the coefficient of x2 is 0 in the first equation and the coefficient of x2 is 1 in the second equation.
Okay. Okay.
Okay, but for the first case we already saw that the coefficient of x2 is already 0 from before only, so we need not do any row operation on the first row. So we only need to do, that is one thing, and that is for the second equation we divide by 2 to get the coefficient equal to 1 for x2 in the second equation. Okay, clear?
Yes, sir.
So we did this row operation, like we divided by 2. Now we have the final. Now, yeah, also the coefficient of x2 should be 0 in the final, that is or optimize, that is objective function also. You can here I can show again, wait. Here also, yeah, you can see that is the objective function is a function of non-basic variables. The coefficient of all the basic variables is 0 for the objective function. So you have to convert the value of x2 equal to 0 for the objective function also. Initially, what was the value of corresponding to x2 in the objective function? It was -3. Now we have to do the row operation of this third row with respect to the second row, because here we need the coefficient of x2 as 1 and and we need the coefficient of x2 as 0 in the third row, that is objective function. So how can we do that? It will be this, if we consider this as r3, if you consider this row as r3 and this is as r2, it will be what? R3 plus 3 by 2 into r2, right? -3 plus 3 by 2 into 2 will be 0. So once we are doing this, we have to do for the all the elements in that in the objective function, that is the third row. So what we have done here is we have it is r3 plus 3 by 2 into r2, and this r2, remember, is the initial r2, not after changing. Okay, so this row we got after doing the row operation. This is r2 dash, like the second. In this r2 that I am doing is for the initial one. Initially what we will be doing all the row operations based on the values of coefficients of this initial matrix only. So how it will get after doing this row operation, it will be for the first for x1 it will be -2 plus it will be -2 plus 3 by 2. So -2 plus 3 by 2 is how much? Minus of 0.5. So we'll get -0.5 here. We'll get 0 in this second, again 0 in the third, because 0 plus 3 by 2 into 0 is 0, and for the fourth row 0 plus 3 by 2, that is 1.5. And how to will get for the value of objective function? Now in this case what we said, we told that x2 and x3 are the basic solution, but x1 and x4 are the non-basic solutions. So f is already a function of f equal to -2x1 minus of 3x2. So we have x1 is already equals to 0. So f is equal to minus of 3 into x2, and x2 value we got as 5. Because how did we get the value as 5? If we from this equation we have only the coefficient of x2, all the other variables are we have x2 and x3 as the basic variables, and we do x1 and x4 are the non-basic variables. So we'll be setting the value of non-basic variables as 0. So if we set the non-basic variables as 0, in that case we will have only x2, and x2 is equals to 5. Okay, clear? So that's how we get the value of x2 equal to 5, and from the first column we have x3 as the basic variable, so we'll be setting x1 and x4 as 0, and x2 coefficient is already 0, so x3 is equal to 6. So we'll get the solution of the basic variable, that is x3 equal to 6 and x2 is equal to 5, and the value of f can be obtained in this from the initial value, that is minus 2x1 minus 3x2. x1 is already 0 because it is a non-basic variable, and minus 3 into x2 value is 5 is equal to minus 15. So yeah, okay, now we will see if we can further improve this solution. Yes, we can further improve, because you can see there is again a negative coefficient in corresponding to x1. x1 is the non-basic variable, and there is already a negative coefficient in the objective function corresponding to the non-basic variable x1. So we have to consider x1 into the basic variable, and to consider x1 in the basic variable, again we will see this bi by aij. It is for the first row it will be 6 by 1 corresponding to x1 is 6, and the second row is 5 by 0.5 is 10. So x1 will be coming in place of x3 as the basic variable. Okay, so now as x1 goes into the basic variable in the first row, so we will need to have the coefficient of x1 in the second row as 0. So we will do the row operation on the second row and the third row. Again for the third row also, that is for f also, we will need the coefficient of x1 equal to 0. For the first row we did not do any operation since the coefficient of x1 is already 1. So we will keep the first row as it is, that is whatever we have. Now for the second row we will do the row operation as r2 minus of 0.5 of r1, because 0.5 minus of 0.5 into 1 is 0. So if we do this row operation, we will get 0 corresponding to x1. For x2 there will be 1 only. For x3 it will be minus 0.5. For x4 it will be 0.5, and f is equal to 0. And for bj it will be 5 minus 0.5 into 6, that is 5 minus 3 is equal to 2. Okay, and for the third row, that is for the objective function row, we will do the row operation as r3 plus 0.5 r1. Why? We have it is minus 0.5. If we add 0.5 into first row, we will get the value of a coefficient of x1 corresponding to r3 will be 0. So we do this operation, we get 0 here. Again for x2 we will be getting 0, and for x3 and x4 we will have 0.5 and 1.5. Now what are the non-basic variables here? Here x3 and x4 are the non-basic variables, and the coefficient of x3 and x4 are 0.5 and 1.5, both are positive. So in this case we cannot further improve the solution. We will just because both the coefficients are positive, so x1 and x2 are the basic solution, basic variables, and the value of x1 and the basic solution is, that is value of the basic variables is x1 equal to 6. Here because here x1 is coefficient of x1 is 1, we will set x3 and x4 equal to 0, we will get x1 equal to 6, and from the second equation we have get x2 is equal to 2, as we set x3 and x4 equal to 0. So we have the values of x1 and x2, we substitute in the objective function, that is minus 2 into 6 minus 3 into 2, we get minus 18. So the minimum value of the function that we get is minus 18, and we won't be able to minimize it further. So this is how we have done do the simplex method. Okay, so if you have any doubts in this whatever steps I've discussed, you can ask me now, and then we'll proceed to some like previous year questions. Okay, then if there are no doubts, we'll proceed further. So, which of the following is not true? So, I hope you can. Which of the following is not true for a linear programming problem? Slack variable is a variable added to the left hand side or for less than equal to constant to convert it to equality. Yes, this is already true. A surprise variable is a variable subtracted from the left hand side of a greater than equal to constant to convert it to equality. Yes, this is also true. A basic solution, which is also in the feasible solution, is called a basic feasible solution. Yes, it is also true. The fourth option is a column in the simplex table that contains all of the variables in a solution is called the pivot or a key column. No, the fourth option is the correct option. So, and if we do a graphical, so this second question is about a graphical solution, that the value of our objective function is maximum under linear constraints. At what are the scenarios? At the center of the feasible region? No. At any vertex of the feasible region? No, it cannot be maximum at any vertex. At 0, 0, obviously no. The vertex which is at maximum distance from 0, 0. So in that case, the solution will be at the objective function will be maximum under linear constraints. We will see that in this example. So we need to find what are the equations that represent this shaded region. The shaded region is represented as, so one equation is it should be less than equal to 2x plus 5y equal to 80. So 2x plus 5y should be less than equal to 80. So it should be either 3 or 4. And also the second constraint is it should be less than equal to x plus y equal to 20. So x plus y less than equal to 20. And here x is greater, y is greater than equal to 0, x is greater than equal to 0, and also y is greater than equal to 0. So the third option is 2x plus 5y less than equal to 80, x plus y less than equal to 20, and x greater than equal to 0, y greater than equal to 0. Okay. Next, we have to solve this equation by graphical method. So we have to maximize z equal to 3x plus 5y subject to this constraints, that is 3x plus 2y is less than equal to 18, x less than equal to 4, y less than equal to 6, x greater than equal to 0, and y greater than equal to 0. So we'll just draw the solution here. So the first constant is 3x plus 2y less than equal to 18. So to consider this line, how do we get the vertex point? If we consider y equal to 0, then x is equal to 6. If we consider x equal to 0, then y is equal to 9. So we have the vertex points for this. Suppose if we consider 6, 7, 2, 3, 4, 5, 6. I am not drawing properly to scale. Four, 5, 6, 7, 8, 9. So x is equal to 6 and y is equal to 9. So the line will go somewhat like this. So this is one constraint line, and what is the value should be less than equal to this. So less than means it will be in this region. So this is one condition. The second is x is less than equal to 4. X less than equal to 4 is this region. If we just do this, we will have this region. We have one vertex point, and the second is y less than equal to 6. Y is less than equal to 6. Now we need to find we already saw in the last problem that the maximum value of objective function we can get at a vertex point, that is at farthest distance from the origin. So it can be this or it can be this. Since this is the total final feasible region. So in this case, we will see what are the coefficient of this point. In the here, y is equal to 6. If we substitute y equal to 6 in this equation, we will get x equal to 18 minus 12 by 3. X is equal to 2. And for this point, we have x is equal to 4 already. If we substitute x equal to 4, y is equal to should be 3. Yeah. So we have 2 points, that is 2, 6 and 4, 3. So we have to maximize 3x plus 5y. So for the first point, z is equal to 3 into 2 plus 6 into 3x plus 5. Five into 6 plus 36. And the second problem is z is equal to 3 into 4 plus 5 into 3. 12 plus 15. 12 plus 27. So the maximum value is 36. So z equal to 36 at x equal to 2 and y is equal to 6. Okay, I hope it's clear. Okay, then we will move to the next question. So here is just a sample problem. Suppose if we have to minimize f equals to sigma j equal to 1 to n, I equal to 1 to n, Cij, Xij is subject to uh, two different equations of constraints. The first equation is Cij, Xij less than equal to Ai, and I equals to 1 to m. So there will be m equations here. For I equal to 1 to m, we will have m equations, and j goes from 1 to n. J is the number of variables. And the second equation we have when j goes to 1 to n. In this case, there will be n equations, and I is the corresponding value of for each of the coefficient. So we will have how many total constants? The total number of constants will be the sum of these two, that is m plus n. This is just simple. Okay. So now we have a set of problems. So here we are given a problem. We have to formulate the problem, and then we have to solve it using simplex method. And also I will show the solution to do in how to do in Excel solver. That is a brief demonstration. Okay. So how do we frame the equations? The question is, in a semester exam or hydrology course, there are two types of questions to be answered: short answered and long answered. Relevant data is given below. That is for the short answer. The time taken to solve each short answer question is 5 minutes. For marks is 3, and number of questions is 10. And for the long answered question, the time taken to solve one long answered question is 10. Marks is 5, and the number of questions is 14. So the total marks is 100. And student in total time is equal to 3 hours. Okay, so we have to solve the equation. So let x be the number of short answer questions, and y be the number of long answer questions. So first we need to identify the objective function. So the objective function will be what? We need to maximize the marks to secure maximum marks. So get the maximum marks, we have for each question we have 3, each short answer question we have 3 marks, and for each long answer question we have 5 marks. So the objective function f is equal to 3x plus 5y. So this is a maximization problem. So we already discussed that we will convert all our problems to minimization problems. So we will write our objective function in the form of minus 3x minus 5y, and we will do the minimization. Minimize f equal to minus 3x minus 5y. Okay. So we got the objective function. Next is we have to do the find the constraints. How do we find the constraints? So the thing is that we have the constraint on a total number of marks obtained by a student, and also have a constraint on the total amount of time. So we can set one constraint on time and one constraint on constraint on the number of questions that is solved. So the first constraint will be based on time. We can say that 5 into x plus 10 into y should be less than equal to 3. Sorry, we have to convert this to minutes. So yeah, time taken it is given in minutes, 5 minutes, so total time is 3 hours, so 3 hours will be 180 minutes. So the one first constraint is, that is 5x plus 10y should be less than equal to 180. It is total amount of time should be less than equal to 3 hours. Then the second condition is the maximum number of x. The maximum number of questions that can be solved for a short answer and long answer is also given. That is, you cannot solve more than 10 short answer question and cannot solve more than 14 long answered questions. So second is x less than equal to 10, 3 is y less than equal to 14. Okay, and the final constraints are x greater than equal to 0 and y is greater than equal to 0. Why? This is decision variable should be greater than equal to 0. So we have formulated the problem. This is our objective function and these are our constraints. So we will match for the first problem is the linear constraints except x greater than 0 and y greater than 0, and the objective function z are, so we founded z is equal to 3x plus 5. It can be 1 or 4. And the second constraint is 5x plus 10 less than equal to 180. That is fine. And the other two constraints are x less than equal to 10 and y less than equal to 14. So it is the first question. Okay, then the second part is the vertices of the feasible region of this equation are. Okay, so if we, this is only again we can do in this using the graphical method. So the first constraint is 5x plus 10y equal to 180. So if we set x equal to 0, we will have y is equal to 18. So 2, 4, 6, 8. Twelve, 14, 16, 18. So, oh sorry, it should be y is equal to 18, right? Sorry. So y axis should go till 18. Okay, I'll just do the diagram here. So it's not up to scale obviously, so if y equal to 0, x is equal to 5 into 36, right? 36. So if we take the scale of 6, 12, 18, 24, 30, 36. 6, 12, 30, 36. So the initial value is y is equal to 18 and x is equal to 36. Okay, the second is x is less than equal to 10, y is less than equal to 14. So okay, so one of the other constraint is x is less than equal to 10, and so in this point if is x is equal to 10 what we will get from this line equation, it will be y is equals to 180 minus 50. It will be 13. So y is equal to 13. And the second equation is where y is less than equal to 14. So y is 14 here. So if y is 14, x is equal to 8. So we got the 2 points where we can get the optimal solution. One is 8 comma 14, another is 10 comma 13. So it is the third option, that is 10 comma 13 and 8 comma 14. The maximum value of the objective function in the above equation is, you can Excel solver, you can use the Excel solver, I will show that. And also we can try simplex if you want. Okay, we will do the simplex method for our next question. For this question I will do the Excel solver, and also I will show from the graphical values. So we have 2 points. One is x equal to 10, y is equal to 13. So z is equal to, that is optimal objective function is, we were taking maximization directly only. 3x plus 5y equal to 30 plus 65 is equal to 95. And our second is x equal to 8, z equals to 3 into 8 plus 95. So the maximum value of z is 95. The feasible solution is x equal to 10 and y equal to 13. Okay, I'll show this in Excel. Just a minute, I will open my Excel. Can you see my Excel sheet? Okay. Okay, what we have, the we'll first mention the variables. So we have x, and y. We have variables x and y. We initially will keep it as 0 and 0. We are not setting any value to these variables. Next we have the objective function. So objective function f is equals to, what is the objective function? We have 3x plus 5y equal to 3 star x plus 5 star y, right? Okay. And the constraints. So the constraints, the first constraint is, we mention as g1. So the first constraint is 5x plus 10y is less than equal to 180. So we will write is equals to 5 star x plus 10 star y. Okay, this is the left hand side, 5x plus 10y and less than equal to 180. Okay, the second constraint is x is less than equal to x is less than equal to 10, and the final constraint g3 is y is less than equal to 40. Okay, we have to optimize this, so I will do is using Excel solver. We go to data and okay, I don't think I have solver, so I'll just install the solver add-in. We will go to add-ins, we will find add-ins, we have solver add-in, we'll press OK. Okay, so solver is added to the add-in. We will go to solver. Okay, so set objective, so it will set the objective function. I have already set the objective function. I have to select that cell. We'll go here and select this cell. We'll press OK. What you have to do, it is a maximization problem. I already told you to maximize the marks, so it is max by changing the variable cells. What are the variables that we are taking? We are taking x and y, and variable values of variable are these two cells. We will select those two cells. Okay, now subject to the constraints. What are the constraints? We will be adding one by one. We will go to add the cell reference. So cell reference is the left hand side. So the first layer here is the for G1 constraint, which is the left hand side, is less than equal to we have, and the constraint is the this 180. Okay, we will add, we have added the first, then we will add the second one. Second is x, we will select this, and here we will select this. Okay, we will add, and the third constraint is this one, is less than equal to this, so add. So we have added three constraints, and we have also made it make unconstrained variables non-negative. What we will do, we will use the simplex method for solving here, and we will click on solve. So the solver has found a solution. There is no error, so we can see the answer. What is the answer that we got? So go to the answer report. So you can see here that the optimal value that we got is 95. This is the time required for solving. This is 0.000001 seconds. Precision is 0.00001, time is 0.016 seconds, and the value of x is 10 that we got from graphical method. The value of y is 13, and these are the values of the slack variables that we get. These are the constraints, and out of the equation of constraints later is set here. Okay, I hope this is clear now.
Selecting the variable, we have to select one by one, or you can combinedly we can select both two also at a time.
Two at a time we can select.
Okay.
So I selected like the values. Just select the cells right in the Excel. So you can select if there here it is two variables. If there are more than two, you can select all the variables and put it in the solver while selecting the variables. Okay, but for constraints and the equation, the constraints you have to select one by one, not together.
Okay. Okay.
Okay, let's come back to the writing part. Screen here. Okay, So yeah, I did that using Excel solver, and we'll see the final question for today. So consider a linear program consisting of two variables x and y satisfying the following three constraints. So this problem is given, that is x plus y less than or equal to 10, y greater than or equal to 4x minus 20. So we'll write the constraints in the proper standard form. X plus y less than or equal to 10, 4x minus y is less than or equal to 20, x plus 3y is less than or equal to 24, and finally x comma y is greater than or equal to 0. So these are the constraints. The maximize the function is 4x plus y. We have to maximize, so we'll convert it to a minimization problem. Okay. So number of slack variables while solving the above problem by simplex will be, what will be the number of slack variables? The number of slack variables will be equal to number of constraints. So we'll be needing one slack variable here, one slack variable here, and one slack variable here. So we'll needing 3 slack variables. So it will be 3. The value of the objective function after first iteration and the final iteration. For that we have to solve the simplex. So let us do it. So initially we will write the constraints again, x plus y plus, okay, we will write as x1 is equal to 10 plus to 20, x plus 3y plus 3 is equal to 24. So we have the three equations now, x1, x2 and x3. So as we, since we have the three equations, we have converted to equality form, we can write the simplex table now. So initially we will be considering x1, x2, x3 as the x1, x2, x3 as the basic solution, and x and y as the non-basic solutions. So basic solution will be x1, x2, x3, x, y, x1, x2, x3. Value of f, bi. Okay, for the first equation, if the coefficient of x is 1, y is 1, x1 is 1, x2 and x3 is 0. For the second equation, it is 4 minus 1, 0, 1, 0. And for third equation, 1, 3, 0, 0, 1. F will be 0, 0, 0. B is equal to 10, 20, 24. And for the f we have minus 4 and minus 1. So minus 4 and minus 1 here, 0, 0, 0. And the value of f is initially 0 because both x and y are non-basic variables, so the value will be 0. Initial basis x1, x2, x3. And the solution for x1 is equal to 10, x2 is equal to 20. Now we have corresponding to f, x is a non-basic variable and the coefficient of x is negative, maximum negative, so x will go into the basic solution. So x will replace which of the variable we will see by the term bi by aj. For the first row, it will 10 by 1, so 10 by 1 is 10, 20 by 4 is 5, and 24 by 1 is 24. So x2 will be replaced since it is least, the value is least among the other two variables values. So x will go in place of x2. So as x is going into x2, in this case what happens? So the coefficient of x in the second row should be 1, and the coefficient of x in the other two rows should be equal to 0. So we have to do the row operation in that way. So we'll write the table. So x1 is already there. X. Now, yeah, for the second row we will be dividing it by 4, so that we get the value of coefficient of x is equal to 1 here. So if we mention this as r1, r2 and r3, so initially we'll have r2 by 4, so it will be 1 here, minus 1 by 4 in the second variable, 0 here, 1 by 4 here, and 0 here. Here also 0, and for 20 by 4 is 5. Okay, now we have to get 0 in this first row. So it will be what? r1 minus of 1 by 4 of r1 minus 1 by 4 of r2. So what we will do the row operation here, r1 minus 1 by 4 of r2. So we'll get the value, first value will be 0. Now for y, 1 minus of 1 plus 1 by 4 is equal to 5 by 4. 1 minus of 0 is 1. 0 minus 1 by 4 minus 1 by 4. This is 0. F is 0. This is 10 minus 20 by 4. 10 minus 5 is 5. Okay. Similarly, for r3 also, to get the value of coefficient of x equal to 0, we will do r3 minus of 1 by 4 of r2. So what we will get? It will be 0 here. 3 plus 1 by 4. 13 by 4. And in the second is 0 minus 0 is 0. 0 minus 1 by 4 minus 1 by 4. This is again 1 minus 0 is 1, 0. And 24 minus 20 by 4, 24 minus 5 is 19. And yeah, we also have to get 0 for the f row also. So for the f row, it will be what? Just adding this, we mentioned this as r4. It will be r4 plus r2. Minus 4 plus 4 is 0. So we'll have, just do here, this r4 plus r2. So this will be 0 here. Minus 1 minus 1 will be minus 2. As in 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 1 is 1, and again 0 plus 0 is 0. So, and what is the value of f that we will get here? So here we have set x, x1 and x3 as the basic solution, y and x2 non-basic. So as y and x2 are non-basic, so y equal to 0, x2 equal to 0, and if for the basic solution what we will get, x is equal to 5, x1 is equal to 5, and x3 is equal to 19. So we have x is equal to 5, and what was our objective function, equal to minus 4x minus y, so y is 0, is equal to minus 4 into 5 equal to minus 20. So the after first iteration we will get the value of f as minus 20. So if it is minus 20, it is, if we do maximization problem, it will be plus 20 since we converted to minus. So we can go directly with the final option, that is 20 and 20, since all the other options are not matching, but still we will do one more round of solution to get the final solution. So now what we see, we have that corresponding to y, the coefficient is negative and all other coefficients are positive. So we can, so y will go into the basic solution. So which variable y will replace, it will depend on the b by aij. So it will be 5 by 5 by 4, so it will be 4. 5 by minus 1 by 4, it will be minus 20, so this won't come into consideration, this is already unbounded. And the last is 5 by 13 by 4, so 20 by 13. So 20 by 13 is the least positive value, so y will go into x3. Y will go into x3, so we'll write the simplex table in that way. X, y, x1, x2, x3, f, b, and b by a and g. So x1 will be here only, so x will be here and y will go into the third equation. Now if y goes into third equation, the coefficient of y is here should be 1 and the coefficient of y in these two should be 0. So to get the value of coefficient of y equal to 1 here, we will divide this R3 by 13 by 4. So by 13 by 4. So this will be 0, this will be 1. Again I think x1 will be 0, x2 will be minus 1 by 4 minus 13 by 4, minus 1 by 13, minus 1 by 13, and I think x3 will be 1 by 13 by 4, which is equal to 4 by 13. F will be 0 and b will be 19 by 13 by 4, 4 19s are 19 3s are 57, 76, 30. Okay, and it is 1. Yeah, we got the value of y, equation for y. Now we need to get the value of the second row, the corresponding to coefficient of y corresponding to second row is 0. So what we should do, you have to multiply second row by 13 and add it to the third row. 13 by 4 minus 13 by 4, 13 by 4 is equal to 0. is equal to R4 plus R3. So this will be 1, this will be 0. This will be 0 again. So 13 by 4 minus 1 by 4 will be 3. Next there will be 1, 0 plus 1 will be 1. F will be 0 and 65 plus 19 we will have here. So how much is 65 plus 19? 84. We will have 84 in this. Okay, and for the first row we need again 0 here. So we have to do what? X1 plus 5 by 13 into R3. R1 dash plus 5 by 13. The 5 by 13 into R3. So there is 0, 0 here. So 1 plus 5 by 13 into 0 is 0. For x2 again minus 1 by 4 plus 5 by 13 into minus 1 by 4. Minus 1 by 4 minus 30 minus 18 by 52. Minus 9 by 26. x3 will be x1 plus 5 by 13, so it will be 5 by 13 only. F will be 0 and B will be 5 plus 19 into 5 by 13. Five plus 19 into 5 by sorry, this is minus, right? Sorry. It's 5 minus 19 into 5 by 13. So this will be minus 1 by 4 plus 5. So and B will be 65 minus so we have this, and for the final this column again what we have to do for the last row. So F is corresponding to F, the coefficient of Y is minus 2, so we have to do it to 0, so minus 2 into 13 by 8. R4 into 13 by 8 plus R3 be 0 0. And for the final for x2 it will minus 1 by 4. This will be 11 by 8. And the value of the objective function we can see. So there are no negative values here again, so we have already found the optimal solution. So what will be the values of x and y? X is equal to 84, y is equal to 76 by 13. I think there might be some equal to 5 there. R2 into 13 by 4 plus R3. I think there might be a calculation mistake here. Y is equal to minus 1 by 4 plus R3 minus 1 by 4 into R2 plus minus 1 plus 3 plus minus है तो प्लस ही होगा. 13 by 4 and 19 only. So if it goes x here, 76 by 13 goes. And for this column, R2 into 13. Two into 13 plus okay, instead of this operation I think we have did one mistake here. It shouldn't be R2 into 13 plus R3. We should go with R2 plus 1 by 13 into R3. We do all the operations with the pivotal row, that is this row. So this will be 0 here. So minus 1 by 4, what is for this column, 1 by 4 minus of 1 by 52. So 1 by 4 minus 1 by 50. 12 by 52. So this is equal to 12 by 52. This will be 1. This will be 1 only, and this will be 5 plus 19 by 13. So this value will be 5 plus 19 by 13. 65 plus 19 is 13 is equal to 84 by 13. So we have these values here. So we got x and y. X is 84 by 13 and y is 76 by 13. Therefore j is equal to minus 4x minus y. We take minus comma 4 into 84 by 13 plus 6. We take 13 as denominator. 4 4 is 16. 6 plus 6, 12, 7. 412 by 13, and I think this value will come out as 30 point something. It will come. So it will come something like that. So I think in this we did work. I think there might be some calculation mistake here. So it is coming somewhere near 28, but not exactly 28. So I think you understood the procedure, right? So what is the procedure of simplex method? I explained 2 times. So if you have any doubts, you can ask me else in today's session.
While putting that f function in the last row, we have to calculate with these constraints x value and y value, calculate the f, or for f also we have to do the row operation for f.
Like, can you repeat what you're asking?
While doing the row operation,
Yeah.
regard for that f column,
Yeah, yeah.
the objective function, we have to calculate the with the values. You have to calculate the function, or there also you have to do the row operation for f, calculating f column.
For the f column, we do the row operation, because we have to finalizing when we are doing this formulating the problem. There is a proper method, like I told you. Yeah, here you can see we have to get all these equations will come into the simplex, and all the constraints, and finally the f equation.
Okay.
So everything will come into the constraints.
Okay.
In the f equation, all the coefficients of the basic variables will be 0, and the coefficient non-basic variables will be non-zero.
Okay.
That's what. But when we get the value of the function will be depending on whatever the basic variables that we get. Okay. Like basic variables are whatever function it is first defined. Suppose if f is a function of x and y, or something x1 and x2, so the value of x will be based on that, whatever the value of x1 and x2 we obtain from the simplex method.
Okay.
Okay.
Yeah.
After doing every iteration, we will get the values of the non-basic variables as well as the basic variables, and after getting the values of all the variables, we can obtain the solution of the, that is the value of f based on the objective function. That is what is the motive. Okay. Okay, then if there are no further doubts, we can close today's session. Have a good night.